Hello, I'm Seema and welcome to part 17 of the chapter The Solid State. Moving ahead with our discussion of the imperfections in solids and crystal defects. In the previous video, I told you about stoichiometric defects. In this video, we'll be discussing the non-stoichiometric defects and impurity defects. So let us start. Non-stoichiometric defects. A large number of stoichiometric inorganic solids are also known to have non-stoichiometric defects. There's a large number of organic solids which should be in the stoichiometric ratio, but they show non-stoichiometric ratio of their components. That is, the cation and anion are not present in their stoichiometric ratio. Remember, whether there is stoichiometry or there is no stoichiometry, the crystal or the compound will always be electrically neutral. It will always have the same number of positive and negative charges, although the number of cations and anions may not be equal. Yet, the stoichiometry is not being maintained, but electrical neutrality is always maintained. You have to keep this thing, you have to be very clear about this thing. Because if electrical neutrality was not maintained, everything would have given you a shock. Because everything, there is no perfection in the universe. I told you even the best of crystals which are made in nature will not be perfect. There will be some kind of defect even in the perfect crystal. So you can imagine that having non-stoichiometric defects would also be very common. So we say a large number of stoichiometric inorganic solids are known to show non-stoichiometric defects, or they are known to be present in non-stoichiometric proportions, yet electrical neutrality is still maintained. You will understand how electrical neutrality is maintained as I explain the defects to you. Now, the non-stoichiometric defects can exist in two main ways. One is the metal excess defect and the other is metal deficiency defect. In one defect, the metal is in excess and the non-metal or the anion is in deficiency, is less. In the second case, there is a metal deficiency defect, which means the anion or negative charge is, the anionic part is greater and the metal is lesser in it. So let us take the first part, that is the first kind, that is metal excess defect. Metal excess defect can further be due to two reasons. Metal excess could be due to anionic vacancies, or metal could be in excess due to the presence of extra cations on the interstitial sites. So taking the first one now and explaining that. Due to anionic vacancies. When is metal in excess? When there are anionic vacancies. For this, we'll take the example of a sodium chloride crystal. Take a look at this crystal. In sodium chloride crystal, every sodium ion which is positively charged is surrounded by negative charge, which is negatively charged. I forgot to put a plus sign here. That is negatively charged chloride ions. You are aware of this. Now, what happens? The sodium ions or sodium metal, when you start heating the sodium chloride crystal in an atmosphere of sodium metal, the sodium metal, some of the atoms of the sodium metal come and get deposited on top of the crystal of sodium chloride. When the sodium atoms, now they are neutral atoms, they are not ions, they are not sodium ions, they are neutral sodium atoms. They come and they start getting deposited over the crystal. When they get deposited, what happens is that chlorine or the chloride ions present in the crystal, they really want to take that sodium into the crystal. And what they do, they go and they combine with the sodium, one of the chloride ions from somewhere in the crystal. It's not necessarily on the top. Some chloride ion, even from somewhere down there beneath the surface, may get attracted and will start moving, because it will start moving towards the sodium metal. Because sodium metals, all metallic atoms have a tendency to attract electrons. So the sodium metal atom it attracts the negatively charged chloride ion, and the chloride ion goes and reacts with the sodium atom, thereby converting it into sodium ion. It turns sodium, or it ionizes sodium into Na positive, and one electron is lost. The chloride ion is negatively charged, so it goes and it joins with the sodium ion and forms sodium chloride. But what happened? Imagine this red part, the red circle. Imagine that this was the sodium which came to the surface and it got deposited. The chloride ion from here, it moved to the surface, and the red color shows that the chloride ion should have been here, but now this space is empty because the chloride ion went up and it came here and it reacted with the sodium, thereby converting the sodium into Na positive, and the chloride ion, which was negatively charged, combines with it to form NaCl, and the electron which is lost by the sodium atom to make it the sodium ion, it diffuses in and it occupies that empty space. Do you see? A vacancy was created by the chloride ion when the chloride ion moved towards the surface to react with the sodium atom which had deposited, which had come and settled down on the surface. So this vacancy or missing site or vacant lattice site is occupied by that electron. The electron which is negatively charged, it diffuses into the crystal. Imagine if something is negatively charged, where will it go? It would always prefer to go in the center of positive charges because negative is attracted by positive. So this site where there should have been a negative charge is now empty. So that electron comes and it occupies this empty or vacant site. Such a site where electron occupies the center, that center, or the site where the anion should have been there, the electron occupies that anionic site. Such a site is known as F center or Farben-Center in German. I think it was German, you can confirm it from the book. So the Farben-Center means that it is that part or a center which is giving color to the crystal. So this electron which is present in the anionic site, when heated or when it attracts light or when normal light falls over it, it attracts the frequency of it just gets agitated by the energy of the photons, and the electron starts emitting light of a certain color. Therefore, they are known as, such centers are known as Farben centers or F centers. In the case of sodium chloride, the sodium chloride crystal, the F center imparts a yellow color to sodium chloride. If the crystal was lithium chloride, the F center of lithium chloride crystal imparts a pink color. And if the F center is of potassium chloride, it imparts violet color to the crystal. The F centers are responsible for imparting color. So it kind of in light, in natural light or sunlight, or if you put light over the crystal, it reflects that light with the certain color, thereby imparting a color, glittering. The crystal starts glittering with a certain color, which is yellow in NaCl, it is pink with lithium chloride, and it is violet or lilac in the case of potassium chloride. So now I'll just read this part. Metal can be in excess. Now, do you see here? If you see the stoichiometric ratio, what has happened to the stoichiometric ratio? The chloride ions are the same in number, nothing changed in the chloride ions, but due to the additional sodium which got converted into sodium ions, the number of sodium ions has increased in comparison to the chloride ions. So the stoichiometric ratio of 1:1. For every one sodium ion, there should have been one chloride ion, but now that doesn't exist. The stoichiometric ratio is disturbed and the sodium ion is in excess. So metal can be in excess. So there is a non-stoichiometric defect. The metal is in excess, and the cause of the excess of the metal is due to anionic vacancies which are occupied by electrons, thereby maintaining electrical neutrality. Although the site is vacant, there is no chloride ion, but the electron is balancing out that negative charge. The negative charge is still there, even if the anion, that is chloride, is not there. So alkali halides like sodium chloride and potassium chloride, lithium chloride, when they are heated, when crystals of sodium chloride, we take the example of sodium chloride, you could do it with potassium chloride and lithium chloride too. So we took the example of sodium chloride and we say when we heat crystals of sodium chloride, in sodium vapors, the sodium atoms get deposited on the surface. Some of the chloride ions diffuse to the surface and form sodium chloride with these deposited sodium atoms. Now I have shown you only one example. There can be many sodium atoms on the crystal. And therefore, there won't be just one F center, there would be many F centers due to the formation, due to the adsorption of that sodium, conversion of sodium atom into sodium ion by the chloride ions, thereby giving rise to the F centers. So they diffuse to the surface to form sodium chloride when sodium loses an electron to form Na positive. So sodium will lose an electron to form Na positive. The electron occupies the vacant site. That electron which is lost will diffuse and go and occupy that vacant site which was created, because the vacant site should have negative charge in order to maintain electrical neutrality. So the electron occupies the vacant anionic site which is called the F center or Farben center, and it is, which means color center. It is the center which is imparting color. It is that point at which when light is reflected, it imparts color to the crystal. So it's called Farben center or color center. Sodium chloride is yellow due to its F centers, lithium chloride is pink, and potassium chloride is lilac or violet. So this was metal excess defect due to anionic vacancies. We now come to the second way how metal can be excess. Metals can be in excess, or metal excess defect can also be due to the presence of extra cations at interstitial sites. You do understand the interstitial sites. What is an interstitial site? If this is the crystal, the spaces between the sites, the vacancies or the voids, they are called the interstitial sites. They are not lattice points. They are interstitial sites. What happens when you have a very small cation, like in the case of zinc oxide? If you heat zinc oxide up, the Zn is 2 positive and O is 2 negative. What happens when you heat up a crystal of zinc oxide, which is white in color? It turns yellow in color due to the presence of zinc ions. And what happens in this process is that zinc oxide, some of the zinc oxide breaks down, thereby giving rise to oxygen atoms. Zn2 positive ions are given and half an oxygen molecule and 2 electrons are released. Some of the oxygen turns into oxygen gas on heating, and since it is a gas, it escapes the crystal and it leaves the crystal. When the oxygen, which was the negative ion, 2 negative, O2 negative, when it turns into O2, leaving the 2 electrons, it does not take the electrons with it, it leaves behind the electrons, resulting in the formation of oxygen, half an oxygen molecule for every atom. So those electrons, every oxygen which had 2 negative charges, it loses those 2 electrons and becomes neutral oxygen, and 2 oxygen atoms will form an oxygen molecule and escape from the crystal. Now, as a result of loss of the anion, the cation or the metal becomes in excess, is in excess. In this case, what had happened? Cation had been added to the crystal. In this case, anion has left the crystal. But in both the cases, the metal atom is going to be in excess. That is, the stoichiometry is disturbed and the metal is more than the non-metal or the anion. The cation, which is the metal, is more than the non-metallic or the anionic part. So, let me now read it. Zinc oxide on heating gives Zn2 positive. Zinc oxide, which was white in color, when this happens, when oxygen leaves with 2 electrons, it results in a yellow color. the situation is the same. It is these two electrons which are going to impart the yellow color to it. So due to lost oxygen, Zn2 positive now is in excess, because this oxygen, it will just evaporate, it will go away because it's a gas, it will not stay in the crystal. So Zn2 positive becomes in excess. Therefore, the formula, instead of becoming Zno, now changes to Zn1 plus some amount, whatever is the number of oxygens, let us say X number of oxygen atoms left. Then the Zn will be whatever Zn was 1 plus X. Zn will definitely be more than the oxygen, assuming that X number of oxygen atoms turned into oxygen molecules and left the crystal. So the excess of zinc ions, they move. Now zinc is, cations are usually small in size. So now zinc is in excess. So what happens? This excess of zinc ions, they usually move into the interstitial sites. They do not occupy the lattice sites. Like here, the sodium was still occupying the lattice sites and the electron was diffusing in. Here, the zinc, the excess zinc, it occupies the interstitial, the vacancies between the lattice sites. It does not occupy the lattice points, it occupies the spaces between the lattice points, which are called interstitial spaces. So it occupies interstitial sites, and in order to maintain the electrical neutrality, these electrons are hardly, they are so small that you say they have a negligible size. They only seem to have negative charge, but their size is almost negligible. So the negative charge, wherever there is positive charge, in order to maintain the electrical neutrality, the zinc ions have occupied the interstitial sites. The electrons then go and occupy the neighboring interstitial site. They will go as close to the positive charge as they can so that they maintain the electrical neutrality. So the excess zinc moves into the interstitial sites and the electrons occupy the neighboring interstitial sites. And that is how the electrical neutrality is maintained, but stoichiometry is disturbed. And that is why this is also a non-stoichiometric defect. Now, we have studied two types of non-stoichiometric defects. First is metal excess defect, that is, one type, the metal excess defect. We come to the second type of non-stoichiometric defect, is where the metal will be in deficiency. It is not in excess. So we call it the metal deficiency defect. How is the metal deficiency defect created, or what causes the metal deficiency defect? It has been seen that many solids, when you are trying to prepare the crystals of those solids, it's not easy to prepare the crystal. Metal atoms may be very small in size, but most of them are pretty heavy. They are heavy. So when the crystal is being formed, the anion might be light and the metal might be heavier, due to which the movement of the cation is not as fast as the anion. So when the crystal is being formed, sometimes the metal stays behind. It does not move fast enough to to be included in the crystal. So what happens? Many solids are difficult to prepare in their stoichiometric ratio, and the metal is usually found to be less in ratio. Such deficiency. Now what has happened? The stoichiometry is disturbed. If there was, whatever was the number of positive charges, number of negative charges should be equal. So the number of cations and anions, in a way, should be proportionate. They should be in their stoichiometric ratio. But since the metal could not come completely, therefore the metal is deficient, the stoichiometric ratio is affected. The metal is less and the anion is more. But again, remember, electrical neutrality has to be maintained. So who is going to maintain the electrical neutrality? Whatever metals are present, metal atoms are present in the form of cations, they change their charge. I'll give you an example here. We take this example. For example, ferrous oxide. Ferrous oxide is Fe2 positive, O2 negative, and the formula is FeO. Ferrous oxide is often, when you prepare ferrous oxide, you can never get pure FeO. you will get Fe 0.950. Mostly, it could go up to 0.96 also, which means that iron is slightly deficient O and oxygen is in excess, iron is slightly deficient. So how would electrical neutrality be maintained? We know that ferrous ions have 2 positive charge, but ferric iron has 3 positive charge. So in the crystals, some of the Fe2 positive cations are missing, and the loss of positive charge is made up by the presence of required number of Fe3 positive ions. I'm just reading this out so that I can explain it to you. It's very interesting. What happens, imagine this. This is, I put the 2 positive, the metal deficiency defect, I try to show it like this. The red colored 2 positive is the cation, that is ferrous ion. And the 2 negative are the oxides, that is O2 negative. Now, look here, there are 4 2 positives, Fe2 positives and 4 O2 negatives. Now imagine that instead of the Fe2 positive, 3 of these Fe2 positives, let us say one Fe2 positive, the metal did not come into the crystal. Now what is going to happen is that 2 of these Fe2 positives will turn into Fe3 positive, ferric ion. They'll turn into Fe3 positive. What was present was Fe2 positive, right? If 2 of these occupy 3 positive, Fe3 positives occupy 2 of these sides, one side is empty now. The Fe2 positive did not enter, but 2 of these Fe2 positives turned into Fe3 positives. Now look at the number of positive. 3 of the Fe2 positives would have how much positive charge? 6 positive charges. Every Fe2 positive ion has 2 positive charges. So 3 Fe2 positive charges should have had 6 positive charges. And 2 Fe3 ions will also have 6 positive charges. So number of positive charges has been maintained, but the ion has changed from Fe2 positive to Fe3 positive. So for every one Fe2 positive which is lost, 2 Fe3 positives, 2 of the Fe2 positives are substituted, or in place of them you get Fe3 positive ions, thereby maintaining the electrical neutrality. And that is what causes, and this is the vacant site. Now let us read that sentence again. In the crystals, some Fe2 positive cations are missing. Some Fe2 positive cations are missing. And the loss of positive charge is made up by the presence of the required number of Fe3 positive ions. If one Fe2 positive is missing, then 2 more Fe2 positives will have to change. 2 Fe2 positives would change into Fe3 positives, thereby maintaining electrical neutrality. For every 3 Fe2 positives has 6 positive charges, and 2 Fe3 positives also have 6 positive charges. Therefore, the number of positive charges should remain the same. For 3 Fe2 positives, 2 Fe3 positives can do the same job of imparting 6 positive charges. But the stoichiometry is disturbed, and therefore this is a non-stoichiometric defect. So this was about non-stoichiometric defects, and the next is impurity defect. So give me a minute, let me change what I've written on the board to explain impurity defect to you. Alright, so now we come to the third kind of defect, that is impurity defect. We have already done stoichiometric defects and non-stoichiometric defects. This is the third category, that is impurity defects. And I briefly told you what it is. In both stoichiometric and non-stoichiometric defects, the defect is not due to an external source. Or rather, in the case of stoichiometric defects, in the case of non-stoichiometric, as you can have the metal excess due to incoming metal, although it is the same metal, yet you would not call it intrinsic. The stoichiometric defects are intrinsic in nature because whatever defect is there is due to the components which are already present. Impurity, on the other hand, as the name suggests, impurity is something that does not belong to the compound. So sometimes when the crystal is made in the presence of a compound which can become an impurity, that impurity is embedded in the crystal. And such a defect is known as an impurity defect. An example is that if you take molten sodium chloride, molten means in the liquid form, when it is melted, heated so much that it turns into a liquid. If molten sodium chloride contains a little bit of strontium chloride and it is crystallized now, then some of the strontium chloride also crystallizes along with the sodium chloride. Now, the sodium ion has one positive charge and strontium has two positive charges. So for every sodium there should be one chloride ion, but for every strontium there should be two chloride ions in order to maintain the stoichiometry or to maintain the electrical neutrality, both. So if molten sodium chloride containing a little amount of strontium chloride is crystallized, the chlorides, you can't tell, whether the chloride came from strontium or it came from sodium chloride or did it come from strontium chloride. But the thing is that strontium has two positive charge and sodium has one positive charge. So what happens when it is crystallized, some of the strontium atoms will occupy the sites of sodium. So let us take a look at this. Sodium chloride, if it was pure, it should have been like this, that every sodium should have a chloride. Every sodium chloride, sodium chloride, sodium chloride, sodium, and they are every sodium is surrounded by chlorides, and every chloride is surrounded by sodium, and the number of sodium in chlorides is equal. If strontium is present as an impurity, what is going to happen? One of the sodiums is going to be replaced by strontium, Sr2 positive. Now the problem is that this is 2 positive, but sodium is 1 positive. So for every strontium, another sodium is lost, or it cannot be there. Obviously, it will not occupy a site, thereby creating a vacancy. For every 2 sodiums, there should be 1 strontium. So for every 2 sodiums, there should be 1 strontium. That is the ratio in order to maintain the electrical neutrality. But what happens as a result of this? The impurity is present, 1, and vacant sites are created. So let me just read this. If molten sodium chloride containing a little amount of strontium chloride is crystallized, some of the sodium sites, Na positive sites, are occupied by Sr2 positive ion, strontium ion. Each strontium ion, Sr2 positive ion, replaces 2 Na positive ions. For every strontium, it takes 2 sodium ions have to be removed for 1 strontium ion to be present. So each strontium ion replaces 2 sodium ions. And it occupies the site of one of the sodium ions, while the other sodium, which has been kicked out, is left vacant. So it occupies one site and the other remains vacant. The cationic vacancies thus produced are equal in number to the strontium ions. Obviously, for every strontium, there will be 1 vacancy created. So in the entire crystal, if there are let us say 10,000 strontium ions which are present as impurity, there have to be 10,000 vacant sites, cationic sites. Because those many sodium ions will have to be missing in order to maintain electrical neutrality of the crystal. So the cationic vacancies thus produced are equal in number to strontium ions, and obviously the number of vacancies will always be, if there is 1 strontium ion, there will be 1 vacancy. If there are 2 strontium ions, 2 vacancies, 10,000, there will be 10,000 vacancies. Another example of such a solid would be a solid solution of cadmium chloride and silver chloride. Silver again is 1 positive and cadmium is 2 positive. It is the same situation. So if there is silver chloride and cadmium chloride, every cadmium that is present will take the place of two silvers. So one silver, it will take the place of one silver ion, and the other site will be vacant. It will create a vacancy, a cationic vacant site. So these were the imperfections in solids or crystal defects, and the third category, that is impurity defects. With this, our defects are now over, and we'll now be moving to the electrical properties in the next video. So with this, I'll wrap up the video. If you wish to watch other videos of this chapter, please click the link that appears on top of the video. And if you found this video helpful, give it a thumbs up. Subscribe to my channel. Please do recommend it to your friends, because I feel not many children know about my channel. So please help me spread the word, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.